Okay, I'm really excited to see everybody. Thank you all for coming. I'm Michael Koblenz. I am really excited to co-organize this with Jonathan and Will and Luke Church, who I think couldn't make it this time. We have 7 exciting papers today. We also have a discussion at the end, which is then we can kind of discuss whatever issues the community thinks are interesting. We don't have kind of a set agenda for that, so hopefully it should be very interesting and relevant because you get to pick the agenda. So our first speaker today is Shardul Chiplunkar. Did I get their name right? Correct? Yeah, good. Who's presenting diagrammatic notations for interactive theorem proving. So take it away.
Good morning, all. So let's start by taking a look through proofs through the ages. When I say what is a proof, what comes to mind? And let's go all the way back 2,000 years in history, and here's one of the oldest excerpts we have from Euclid's Elements. And this is Euclid's proof of this algebraic identity. But of course, he didn't have algebra back in the day. He only had, text and geometry. And so you see there's a little diagrammatic notation of what he's trying to prove in this on this parchment. Fast forward 1,000 years, because we don't have that much time, we are now solving cubic equations. Again, it's still on birch bark or something. And if you look closely, it's not just text, right? There's these little box notations with text arranged vertically or symbols doing something more than what text can just represent. So this is also a diagrammatic notation. And I'll point out that this manuscript also happens to be one of the oldest recorded instances of the use of the numeral 0, which at the time kind of spanned the boundary between what's a diagram representing the absence of something and what's a textual symbol. Fast forward another 1,000 years, and we get to Leibniz, who's doing a diagrammatic calculus for, I'm not sure exactly what's going on there. But what we do know is that those little pi signs were his way of writing equality. So what's going on here is actually he's doing a step-by-step derivation of some sort, and one line is algebra, and then the next line is also still algebra, but with these little i's and Roman numerals, and something's going on. But yes, more than what just text could express. Now we're entering the modern age. This is a screenshot from the Edmonds and Karp paper, which introduced their algorithm for max flow in a network. And you can see that even the statement of the theorem references the diagram that's printed right above it. And lastly, we're now at the cutting edge of computer science, which is, here's an example of a proof done in separation logic of the imperative program to find the length of a linked list. And you have a loop invariant, and you have a representation of what the list looks like with these little pictures. All right, and finally, we're in 2023. I am told that proof assistants are becoming increasingly popular with computer scientists and mathematicians. So what does the future hold for us? Let's take a look. This is the first thing we're going to see is a formalization of Euclid's Elements in the theorem prover Coq. Okay, fine, you said this is not fair, right? This is geometry, this is mathematician stuff. Maybe these tools are better suited for the sort of stuff we do in computer science. So, all right, let's look at the latest thing I had on my slides before, which is the separation logic proof. All right, you said this is still not a fair comparison because Coq, like many other proof systems, has an incredible thing called notations. And if you have notations, you can make your proof state look much nicer. It looks like this. Okay, and this is fairly workable. It looks like what you would write on paper. It looks kind of like these mathematical descriptions we saw before, but it's still a far cry from this sort of diagram that you really draw by hand or on a whiteboard when you're trying to do this proof yourself or explain it to someone else. All right, so clearly we need diagrammatic notations in our computer-assisted proofs, but they are mostly missing. And to answer the question of why, we're going to learn from a success story, which is text notations or macros, as they're called in Lean or other counterparts of this idea. And we're going to identify 5 principles that we think make them successful. And then we'll speculate on what these might look like in the case of diagrams. So to introduce text notations, I'm going to have this example from separation logic again. You don't need to understand really what all the symbols mean, but it'll be clear what we're doing with this as we go on. So first of all, there's this sep operator that keeps recurring. right? And if I'm writing this on paper, I actually just write a star to indicate a separating conjunction. So I'm going to define a notation which says, well, P1 star P2 is what I mean by when I say sep P1 P2. And okay, we don't have to write the seps anymore, we can write stars. And similarly, now these M cells and M list segs are getting a bit annoying, so I define other notations to notate them with arrows and little curly, with little angle brackets like I would do on paper. And okay, so it's pretty convenient. This looks fairly close to what I want already. What I want to point out in this example is that this was really low cost, right? It did not take much effort to define these notations, and it is not much effort to use them once they're defined. Yet the reward you get from them is pretty high. So this is one thing that makes text notations successful, is their ease, their lightweightness and ease of use. And when we defined these three notations, not only did we define a way to convert that thing into the thing below, but it's a more general notation system, right? If I have some other formula in the same language, in a sense, I can notate it using the same notations without doing any extra work. Moreover, if T2 in this example already has some sort of internal structure or its own notation, then that simply composes with the notation that have additional required. So these notations are compositional, and they're not only are they compositional, but the way they compose is driven by the structure of the object they're trying to represent. And so they're nested and built up in the same way that an object does. So we had these notations, and this looks pretty good already, but now I'm getting tired of writing all the parentheses. And I know that the star is the right associative operator. So I could just say the star is right associative, and we'll have no parentheses anymore. But then I also know that the parentheses around the arrows bind more heavily than the stars, so I don't write those either because I know what it means. So I can give all of these things levels of precedence, and then I don't have to write those anymore either. Lastly, the first notation, which is an infix operator, it's a very common pattern to write these infix operators. So Cog gives me even more concise. I can use the infix keyword, and I can say star means step, and that's it. This is a property of the notation system that I call good-looking idioms. The system provides us these little tricks or little hooks into how things are displayed that make things look good without much additional effort from the user. And imagine if we had to do all this ourselves, right? Sure, maybe we could write all those parentheses, or maybe we could write our own custom parser engine that could, have different levels of precedence and whatnot. But we don't have to because it does it for us. Okay, that's three of the 5 properties I wanted to identify. For the last two, I'm going to switch to a slightly different domain, which is HATRAs. So HATRA is a HATRA, and its root node has 2 children, so it's a height 2, and then one of them is just a node with no children, so it's a head, and then again 2 children, and so on and so forth. And there's a picture, but we're not in the pictures part of this talk just yet, so I'm going to take away the picture. Hydras come from the mythical battle between Hercules and the Hydra, where Hercules, cuts off the head of the Hydra. Sorry for the violence. And well, its immediate parent and siblings realize, and then they react to the damage by replicating themselves some arbitrary number of times. So now we have 5 of them. Notice what happened there, right? I went from this to this. And it was really easy to follow what happened because the part that is not changing, well, doesn't change in notation either. And the part that did change, well, it's easy to see exactly what changed. This is a property I call continuity, where you can easily follow the evolution of an object through proof steps using our notation system. And so you might think, well, nothing about these hydras really says why the order of these children has to be important, right? Maybe I could write it like this, or maybe I could come up with an even zanier notation which talks about the hydra as if it was some sort of, leveled graph. And then I can say when I cut off this head, well, it gets replicated. And well, honestly, at this point, there are so many ways to write the same hydra, so many ways to write the same transformation that if I was just looking at the thing on the right, I would have to do a lot of reverse parsing to figure out, okay, well, are these 2 different representations, 2 different orders of the children the same? Did the same transformation happen? Whereas on the first notation I had on the right, where the order of the children actually mattered, you don't have to do any of that. So the advantages of having this sort of canonical representation is that equivalent objects have immediately identifiable notations, and the same transformation applied to 2 objects produces the same transformation of the notations. This is a property I call canonicity. And it's something in the case of text notations where it's because they're so driven by the structure, we typically have notations that are canonical, that there is really no other way you could have notated the same object, but it gets a bit more tricky with diagrams, as we'll see later in this talk. All right, so we were trying to learn from the success of text notations, and we identified these 5 properties that we think make them successful. What might this look like for diagrammatic notations? And before I go on, I just clarify some non-goals of what we're trying to do here, right? We're not trying to describe what makes a good diagram. Rather, we're trying to describe what makes a good diagramming system. We're also not trying to prove that our diagramming system is better than other tools, mostly because we don't have one. We're just describing, in an ideal world, what sort of system would we want to have integrated with our proof assistance. And lastly, we're not trying to prove that diagrams are better than text notations or something. Of course, both can be appropriate in different circumstances, and we're just saying that it should be equally easy to use whichever one you want to use in a proof assistant. All right, so back to what might these look like for diagrammatic notations. And throughout this section, I'm going to use, so we saw these little blue smiley face diagrams before. I'm going to make slightly different ones with circles and lines instead. And we're also going to use a different notation for the same object, which is these nested boxes. And so throughout this talk, the pictures I'm going to show, we had some custom code to make these pictures. And the code is not the order of the discussion. It's just the diagram's going to serve as an illustration for the principles we want to talk about. But if you want to talk about, what sort of tools we could use to make these, or how they enable or don't different properties, we can discuss that definitely at the end of the talk. Okay, let's talk about structure-driven composition. And let's build up one of these diagrams in a structured way, right? So we start with a node with no children, so a nil is an empty list, and it looks like a circle. So I'm going to have a rule already that says the diagram of a node with no children is a circle. And the little red dashed box indicates sort of the bounding box of this diagram. All right, I have another one, so now there's 2 of them, and I put them in a list. What happened when I put them in a list? Well, the 2 bounding boxes kind of merged into one single bounding box, and those 2 diagrams got put side by side. So my second rule is that the diagram of a cons of 2 things is the horizontal append of the diagram of the first and the diagram of the second. Similarly, when I have a parent node, well, it's a smaller circle, and then when the parent node gets attached to its children, it's a vertical append. So I have my third rule there, which is the same thing as we had before, but vertically. And I would also like to be able to draw, the connecting lines. So while I'm composing these diagrams, I also maintain, I compose a list of their endpoints or the centers of these little circles. And at each level where I combine them with its parents, I can just draw those lines. And so following these 3 simple rules and this, compositional procedure, I can make diagrams of arbitrary depth. And this is, I think, the counterpart of structure-driven composition that we saw for text notations. Now this is very nice, and definitely there is high reward from having these pictures, but is it really low cost? Can we come up with a language that looks, well, this is an idealized language, right? This is not something that we're actually proposing, but can a language to specify these diagrammatic notations actually be as low cost as the infix thing we saw before? Maybe, but definitely I know for sure that this is lower cost than writing this equivalent TIGZ for that diagram. All right. What do good-looking idioms mean in the context of diagrams? And so now here I'm going to explain that little box notation I had before in a bit more depth. These 2 are representing the same hydra. So the red boxes are the innermost children, which are the heads of the hydra, highlighted in red on the left. And the nesting structure of the boxes exactly mirrors the nesting structure of the tree. Now the thing about these boxes is that I can resize them, and their children will adapt to fill the space required. So here's another box, and then I pull it vertically, and it turns into this. And notice what happened here. These 2 boxes that were horizontal before, because now there's more vertical space, they can use that vertical space better by being vertically aligned. I have a video of this. Let's see if this works. I've never done a video in a talk before. Ooh. Oh well. Well, the point is just that we're resizing these boxes, and they reflow to fit the space available. Okay, well, this is pretty cool. How did we do that? And I noticed that, at each level of nesting, these nested box diagrams are actually just grids. And so maybe I'd like to be able to specify a grid layout. And the grid layout has some number of columns and rows, but specified purely in terms of relative proportions, right? 1:2:1. There are no absolute dimensions here. And some gap and some padding at the edges and between the cells. And then when I finally give this grid an actual size, like 200 by 200, it draws itself to produce the picture you see below. If I give it a different size, it draws a different picture. Then I can add items to the grid. I can say there's an item that starts in the middle top cell and extends one cell to the right, and I draw that thing again, and I get this. And I can say, I can tell the grid to transpose itself, which means to treat rows as columns and vice versa, and I can draw the transpose. And so if I compose these at every level, and if I make smart decisions about transposing, where if there's more vertical space you transpose or you don't, depending on the number of columns and so on and so forth, and I divide the children into these grid cells based on how much space they will take up, well, purely compositionally, I can make these sorts of pictures with the box diagrams that I saw before. So to summarize, the idioms here that we used for the box diagrams were grid layouts, and the ability to do transpositions and smart transpositions in layout of children. And the idioms we saw for the trees were, horizontal and vertical juxtaposition, computing bounding boxes and connectors and lines recursively, and being able to nest diagrams with the same interface inside each other. And these are not new idioms. Many diagramming libraries have them. We're just saying that it still makes sense for these common diagrammatic concepts to be available to the user or to the person who is defining diagrammatic notations. Continuity is easy to see with these trees, I think. So we'll do the same thing we did before, where Hercules chops off a head, the rest of it is affected, and it duplicates itself. And that was really easy to see, right? Nothing that didn't change moved on the screen, and the things that did change, well, it was easy to see what happened. But it's kind of a trick, because if I didn't align it so well, it would kind of move around, right? It takes more space. Maybe I'd run out of horizontal space on my screen. So another way I could have done continuity is with these nested boxes, because they always take up the space I told them to take up. So if I go to the next step, it didn't change size, but it did change the internal alignment of the children. So in one way, it's more easy to follow, but in another way, it's not. So different notation systems can have different continuity properties, and I think it's the job of the diagrammatic notation system to enable you to write notations that actually do give you the continuity properties you want. Lastly, canonicity. With the trees, there's one possible diagram per hydra, right? We're considering the one on the left and the one below it to actually be different hydra diagrams. And so the children are ordered both in the syntax of how you define these hydra and also visually in how they're drawn. But with the boxes, it's not so clear. There's multiple possible ways, multiple possible arrangements of children per hydra, and no clear relationship between the syntactic and visual order. All right, so what have we seen here? We've seen that we started with the idea that we definitely need diagrammatic notations in computer-assisted proofs, but they are mostly missing. And to answer the question of why, we looked at text notations or macros, and we identified 5 properties that we think make them successful. And we translated them to diagrammatic notations and saw some examples of what that would look like using our 2 domains for diagrams. Our plan going forward is, things that we have not done and we would really like to do is first to study diagram language design. There's a lot of related work where people have come up with many different ways to write down diagrams and have be generated. So one big domain is for graphs, both the mathematical and the statistical kind, and also languages for notating individual diagrams rather than having notation systems has seen a lot of work already. We also want to study diagram workflows. When you actually work with these in a proof assistant, how does that look like? Can you interact with the diagrams? Can you use them as input? Are they, do they change with things you do to them? Can you write the proof purely by interacting with the diagram? And also on the technical side, what is the best way to integrate with Theorem Prover? And we want to study diagrammatic calculi. So people have been coming up with ways to reason about mathematical domains purely in terms of diagrams and diagrammatic transformations. And I think it would be interesting to really deep dive into one of these and see whether the use or whether having diagrammatic notations available in a proof assistant and how can help that a mathematician or a computer scientist working in that domain. And lastly, we want to build stuff. All right, thank you. Any questions?
All right, thank you so much. We have our first question.
Amazing talk. Sorry, too loud. So yeah, as someone in a research group that works on a diagram text notation or diagram notation tool that is integrated into a theorem proving tool, this is incredibly fascinating. We've been thinking a lot about the continuity question that you bring up lately, and the way that we were initially trying to approach it was you have two descriptions of a diagram. And then you're trying to find the diff between them, both in terms of either in terms of the semantic description of the object you're trying to display, or in terms of the visual or some connection between them. But another way that you could look at it is you could think of, I have one initial diagram, and then I have an operation that I'm applying to produce the next one, right? This would be like if you're doing reductions in a proof or some other sort of valid proof operation in a proof assistant. You're trying to follow the steps, is what you were saying for continuity. I guess, do you have any intuition or initial thoughts about which of those approaches might be more fruitful to try to get better visual continuity, or some trade-offs between those two approaches?
Yeah, great question. And I think this is the first thing you realize when you actually start drawing diagrams, even on a whiteboard, is, well, I keep having to redraw them to make space for what I haven't seen yet, right? So one thing we thought of was, if you have actually finished your proof and you're just replaying it, maybe you can use your knowledge about what the final state of the proof is supposed to look like to draw intermediate steps, leaving space in a sense for what is yet to come. This could be a heuristic where you don't know what the final state is, but you just leave space anyway, just guess what you might need to draw. And the last thing we thought about is we have many powerful UI libraries for doing animation of this sort, where between two steps it doesn't have to be jumpy. It can be smooth, and all that matters is that the user is able to follow what happened, even though visually they might end up in different locations. So there's plenty of directions to play with in that, yeah.
Oh, thank you. So, cool talk. It is a Herculean effort to build a general purpose library for all diagrams. Is Josh in the room? Yeah, talk to Josh if you really want to do that. So what I'm wondering is, if we restrict ourselves to the domain of diagrams for computer-assisted proofs, what is it about that domain that allows us to narrow our problem and maybe more focus this discussion? Or are there properties to the domain of computer-assisted proofs which allow us to make sort of stronger statements about the kinds of diagrams we want to generate, or to eliminate, I don't know, categories of diagram systems that wouldn't make as much sense for computer-assisted proofs? Does that make sense?
Yeah, and so I think one way in which computer-assisted proofs are really different is this strong need for continuity, right? This is a domain in which you really want to do step-by-step evaluation of proofs and see how things evolve over time, which is not always the case for any diagram you draw. Often there's just, sort of the result of a long process of deciding how is the best way to present this, and you have one figure that explains everything about the statement or this theorem or something. So that's one. And another one is that the objects we're dealing with often have a lot of structure internally. So I can go back to this example. These objects have a lot of structure, right? They are not arbitrary diagrams, but they're composed of parts that have a direct correspondence with even the way I would write that in Coq, for instance. And this is not always the case. So I think we can really use the structured nature of these diagrams. And even the layout has a lot of rigidity, I think, that these things are laid out in a line as much as possible, and if they're not, well, there's things we prefer about where the arrows go and where the annotations go that are not the same for a general diagram.
Yeah. Okay, thanks.
Cool talk. I guess I had a question about whether you've thought about how the user, I guess, plays into this, because my experience with this is, even in what you were doing, you're thinking about what's useful to you in your domain, right? And you kind of want those inputs from the user that say, I want a circle to be like the head of my HATRA or whatever. And I guess, like, how are you, and the main problem I see in, I don't know, like, how do you see, like, the user integrating themselves with this kind of diagrammatic like assistant?
Great question, and I think the workflow is actually a really hard question about that we haven't thought about too much in this work. But think about how text notations work, right? The way the workflow for a text notation is that I'm doing a proof. I realize I'm writing something too often, or that I have a way of writing it on paper that isn't being reflected in my proof state. So I come up with, I write a line that says notation blah, and then from that point on, it just works. And both in my input and my output in Coq, I see that notation. So maybe what we can strive for is for diagrammatic notations to be just as easy, where you notice something, even when you're just working by yourself, you're not necessarily trying to present this to someone, but it's that level of ease to just say, well, the diagram for X is such and such, and then from that point on, you use that for your own work.
And I guess I had like a follow-up on this, because I did something with visualizing a proof, and the one thing we saw was that when you're dealing with proofs, you already have your proof script and you have your like goal kind of state, and then you add a diagram to it, and you're adding kind of like another component, and as that diagram gets bigger, it's taking up more space. And have you, I guess, thought about like where it fits in, whether it's going to like replace your textual goal or
yeah, and so maybe we can look at an example where, so so for example, we had one way to do a good integration of geometrical diagrams would be to replace the goal here with, well, I don't know what sum is, but, well, yeah, well, Cong is congruence, right? And so it says that the triangle STU is congruent to CBD. And maybe one way to integrate that would be to, in fact, draw a little picture that says STU and then a squiggly line that says congruence in triangle CBD. Maybe we don't do that for every single hypothesis, only for the goal. Or maybe it's up to you to choose which ones you want to see at any given time, depending on what are relevant to you. But I think it doesn't have to be, or I think we should try for it to not be too much heavier than how text notations integrate into a proof assistant.
Okay, thank you.
So, yeah, in the context exactly of proof assistance, one step can sort of correspond to a lot of different actions, and getting the continuity between the two diagrams is helpful, but when there's so much sort of changing, it can then become hard to track things, and like writing, but also reading proofs. And so, do you have any idea of how we might be able to use diagrams to break things up into smaller pieces?
So I guess, yeah, sorry.
So maybe a more concrete example is, you're using these diagrams to create some abstract notation that then is easier, hopefully, to read, but if you're coming to a proof and reading it, and you might not know that notation, how might you then show that user sort of the intermediate steps, and then once they understand that, they can abstract over it and use the original notation? Did that help?
Yeah, if I understand your question, are you saying that how do you introduce someone who is not familiar with the diagrammatic notation you just invented to what it means?
Yeah, sure.
Yeah, it's a good question. I don't have very many ideas. But hopefully the diagram makes it easier. So at least it's going to be an improvement over not having the diagrams, right? If you just had the textual term like this, it's impossible. And if you had the diagram, maybe at least you start to get intuition. But beyond that, I don't know. Maybe there is more work required. Yeah.
Okay, thank you so much. I think we need to move on to our next talk.